if we consider a function f of the polar coordinates r and theta, and this function is defined over the region R that's bounded above and below by polar curves. So this bottom polar curve A is a function of theta, and this top polar curve B is also a function of theta. So noting that theta is measured from the horizontal axis, this ray is at theta is equal to theta A, and this ray over here is at theta is equal to theta B. And these polar curves are continuous. And we subdivide this polar region using rays and circular arcs. So the sides of these polar rectangles have constant values of r and constant values of theta, compared to rectangles in Cartesian coordinates, where the sides had constant x and y values. Now considering the region R is bounded by the two polar curves and two rays at theta A and theta B, and the boundary is defined such that the function of polar curve A is smaller than that of B for all values of theta between theta A and theta B, and both polar functions are positive. So this is true for all values of theta between theta A and theta B. So essentially the region R lies in a fan-shaped region, as we can see. Now if we choose an arbitrary polar rectangle and index the rectangles that are completely inside the region using index I, then we take the area of the rectangle as delta A subscript I. And if we choose an arbitrary point inside this rectangle, so for example, let's just choose this corner point over here. So this point has polar coordinates Ri and theta I. So this is the radial distance from the pole and the angle theta I to this line. So we can approximate the area of this polar rectangle as a trapezium. So the length of this side is approximately this distance given by Ri multiplied by delta theta, and then plus the length of this side, which is Ri plus delta R. So this length is delta R, and that's multiplied by delta theta, and then taking the average and multiplying by the height of the trapezium, being delta R, gives an approximation for the area of this polar rectangle. So if we simplify this, we get 2 Ri delta theta on 2 multiplied by delta R. So that gives Ri delta R delta theta. And the second term is delta R squared by delta theta on 2. Now if we take the limit as the number of these rectangles goes to infinity, then delta R and delta theta are both going to approach 0. And that gives a better and better approximation to this region bounded by the polar curves and these two rays. So therefore, as R and theta approach 0, this term drops out more rapidly, given this quadratic term. So in the limit, we get the differential area is equal to R dr d theta. And also recall the Riemann sum is equal to the sum over the number of polar rectangles that are completely inside the region of the function evaluated at Ri and theta I, being an arbitrary point in each rectangle, multiplied by delta Ai. So therefore for small areas of these polar rectangles, the finite area of the rectangle is approximately equal to this term over here. And as we saw, this term here disappears in a limit. So as we did previously, we take the limit of the Riemann sum as the number of rectangles lying completely inside the region go to infinity. So recall this limit in general was equal to the double integral of a function, in this case of the polar coordinates r and theta, over the region R. And we see that this differential area element is r dr d theta. So we have the double integral of the function multiplied by r over r and then over theta, which is the iterated integral in polar form. We can evaluate the double integral of a function of the polar coordinates r and theta over region R as an iterated integral. So recall that we multiplied this by r and then integrated over r and then over theta. So first we draw our region bounded by the polar curves. So for example, we have this circle defined by a constant radial function being r equals 1, and this cardioid has a function of 1 plus cosine theta. So this here is the region between those polar curves. So once we've labelled the bounding curves, we draw a ray from the origin that cuts through the region. So first, we're integrating the function with respect to r, so we multiply by r and integrate over r. And the limits of integration are obtained where the ray enters the region and exits the region. So that's at r equals 1 to r equals 1 plus cosine theta. And then we integrate the result over theta. So the theta limits of integration are the smallest and largest possible values that bound this region. So here we integrate from theta is minus pi on 2 to theta is equal to pi on 2. So that covers all the rays that enter and exit the region. So as we can see, in 3 dimensions, our region of integration in the xy plane looks something like this, where the ray cutting this region, drawn from the pole, looks like this, and intersects both bounding curves at these points. Given the double integral of a function of the polar coordinates r and theta over the region R, bounded by polar curves, so in polar form, we had the integral of the function multiplied by r, integrated over r and theta. So if this function is constant and equal to 1, then the double integral of 1 over the region R gives the area of the closed bounded region in the polar coordinate plane. So for example, if this cardioid has a polar function of r is equal to 1 plus cosine theta, and the circle has a radius of 1, so the polar function is r equals 1. So if we draw a ray from the origin and integrate over r first, then this ray enters the region at r equals 1 and exits the region at r equals 1 plus cosine theta. And then we integrate the result over theta. So to cover this entire region, we integrate from theta is equal to minus pi on 2 to theta equals pi on 2. So evaluating the inner integral, we get r squared on 2, evaluated at 1 and 1 plus cosine theta, and then we integrate the result over theta from minus pi on 2 to pi on 2. So that gives 1 plus cosine theta all squared on 2 minus 1 on 2. So that's equal to 1/2 minus a half, which cancel, plus 2 cosine theta on 2 plus cosine squared theta on 2. And using our double angle trig identity, we have cosine theta plus 1/2 by 1/2 by 1 plus cosine 2 theta. And then if we integrate this over theta from minus pi on 2 to pi on 2, then we get sine theta plus theta on 4 plus 1/2 sine 2 theta by a quarter, which is 1 on 8 by sine 2 theta. Evaluated at theta is minus pi on 2 to pi on 2. So sine pi on 2 is 1 plus pi on 8 plus 0, and sine minus pi on 2 is negative 1. So minus minus 1 is plus 1, and we have minus pi on 8, and minus minus pi on 8 is plus pi on 8, and minus 0. So what we get is 2 plus 2 pi on 8, which is pi on 4. Given the double integral in Cartesian coordinates of our function of x and y over the region R, so we integrate over x and y, then we can change this to an integral over the same region in polar coordinates by substituting for x is equal to r cosine theta and y is equal to r sine theta. So we have the function of r cosine theta and r sine theta, and we replace the x dy by r dr d theta. So for example, if we were given a double integral of the function of this paraboloid being x squared plus y squared plus 2 over the circular region, so that's defined by this circle in Cartesian coordinates being x squared plus y squared is equal to 1, where the circle has a radius of 1. So suppose we integrate it over y first, so we use vertical cross sections, and if we solve this for y, we get y is equal to plus or minus the square root of 1 minus x squared. So our limits of integration are minus the square root of 1 minus x squared to the square root of 1 minus x squared. So that's the integration over y. And then integrating over x, we integrate from minus 1 to 1. So when we get to the integration over x, this integral can become difficult. So let's instead integrate by changing from Cartesian coordinates to polar coordinates. So we draw a ray from the origin that cuts through the region. So if we first integrate over r, so we first substitute for x and y, so that's r squared cosine squared theta plus r squared sine squared theta, which gives r squared, plus 2, and we multiply this by r and integrate over r. So the limits of integration are where the ray enters the region, which is at r equals 0, and exits the region at r equals 1. So note that the polar equation of the circle is constant at r equals 1. And then we integrate from theta equals 0 to theta is equal to 2 pi. And that covers the entire region with these rays. And now we can evaluate this integral. So we have r cubed. So that becomes r to the 4 on 4. And 2r becomes 2r squared on 2. Evaluated at r equals 0 and 1. And this result is integrated from theta equals 0 to 2 pi. So what we get is 1 on 4 plus 1 minus 0 minus 0. Integrated from theta equals 0 to 2 pi. So what we get is 1 on 4 plus 4 on 4, which is 5 on 4 theta, evaluated at 0 and 2 pi. So that gives 10 pi on 4, or 5 pi on 2. Write the double integral in polar form for finding the area of this region. So if we take a ray from the origin in this direction at some angle theta, and take another ray from the origin at another angle theta, then this first ray intersects this quarter circle and this horizontal line, and the second ray intersects the quarter circle and the vertical line. So the limits of integration are going to be different in both cases, and therefore we break the region up into two regions. So we have region 1 and region 2. So to get the polar equation for the vertical boundary line, we have the horizontal distance being r cosine theta, and that's equal to a constant. So the polar equation for this vertical line is r is equal to 3 on cosine theta. And for the horizontal line, we have r sine theta being the vertical dimension, being constant at root 3. So the polar equation of this line is r is equal to root 3 on sine theta. So to find the area of the entire region, we can evaluate a piecewise integral over region 1 and region 2. And note that we take our function of the polar coordinates to be equal to 1 to find the area of a region. So integrating over region 1 first, we have the integral from r equals 1, where this ray enters the region, to r is 3 on cosine theta, where the ray exits the region. And we integrate r over r. And then we integrate over theta. So to find our limits of integration, we need to find the angle of this line that's breaking up those two regions. So if we take tan theta is the opposite edge of root 3 on the adjacent edge, so root 3 on 3 is the same as 1 on root 3. So if we draw our special triangle, we have the opposite on the adjacent, so therefore this dimension is 2, and this angle here is pi on 6 or 30 degrees. So we integrate from theta is equal to 0 to theta is equal to pi on 6. And we obtain the remaining area of the region by integrating over region 2. So we first integrate over r from r equals 1, where the ray enters the region, to r is equal to root 3 on sine theta, where the ray exits the region, and we integrate r over r. And then we integrate this result over theta. So we integrate from theta is pi on 6 to theta is equal to pi on 2. And this gives the area of the entire region. Convert the polar integral to a Cartesian integral. So here we have f as a function of r and theta being equal to r cubed by cosine squared theta. So noting the polar form of the double integral is the integral of the function multiplied by r over r and theta. Now in this case, we're integrating from r equals 0 to r is equal to 3 sec theta, or 3 on cosine theta. And r is equal to 3 on cosine theta is the same as r cosine theta is equal to 3. So this is the polar equation of a vertical line at a distance of 3 from the pole. So we're integrating from r equals 0, being the pole, to this line. And the angle theta is from 0 to pi on 3. So from this equation, we have r is equal to 3 on cosine pi on 3. So noting our special trig triangle, where theta is equal to pi on 3, or 60 degrees, so we have root 3, 1 and 2. So cosine of pi on 3 is 1/2, and 3 on a half is 6. And then taking r sine theta gives the vertical dimension of our region. So sine theta is root 3 on 2, so that gives 3 root 3. So the equation of this line in Cartesian coordinates is y is equal to the slope, being the rise over the run, so 3 root 3 on 3, which is root 3 multiplied by x, and plus the y-intercept at 0. And now we can write the integral in Cartesian coordinates. So let's just get rid of this. So if we first take horizontal cross sections, so we first integrate over x. So if we turn this equation around, we get x is equal to y squared on 3. And we integrate to x is equal to 3. And we can write our function as r by r cosine theta squared. So recall that r is equal to the square root of x squared plus y squared. And r cosine theta is equal to x. So we have x squared. And we're first integrating over x. And then we integrate over y. From y is equal to 0 to y is equal to 3 root 3. And similarly, we can write our iterated integral with respect to y first by taking vertical cross sections. So here we're integrating from y equals 0 to y is equal to root 3x. And we're integrating the same function. So that will be x squared plus y squared to the half by x squared. And then we integrate over x from x equals 0 to x equals 3. Let's integrate the following function of x and y over the given region. So recall the equation of a circle is x squared plus y squared is the radius squared. So here we have two concentric circles with a radius of 1, and the outer circle has a radius of root e. And now I can write the polar integral of our function. So we first integrate over r. So we'll write this function in terms of r and theta, and multiply it by r, and integrate over r. So we can substitute for x squared plus y squared, so that gives the natural log of r squared, on the square root of x squared plus y squared, which is r. And we're integrating from r equals 1 to root e. And then we integrate the result with respect to theta. So here we have two concentric circles. So the area of the region between them is obtained by integrating from theta equals 0 to 2 pi. So noting these r's cancel. So if we integrate by parts, we let u is equal to the natural log of r squared. So du is equal to 2r on r squared by the chain rule dr. And dv is equal to dr. So v is equal to r. So we have u multiplied by v, evaluated at 1 and root e, minus the integral of v du, which is 2 dr. And that's integrated from 1 to root e. So what we get is root e, well, the natural log of root e squared, or the natural log of e, which is 1, minus 1, well, the natural log of 1, which is 0. And this integral evaluates at 2r at r equals 1 and root e. So that gives 2 root e minus 2. So what we get is root e minus 2 root e, which is minus root e, plus 2, or 2 minus root e. And then we integrate this over theta. From theta equals 0 to 2 pi. And evaluating this integral, we get 2 minus root e by theta, evaluated at theta equals 0 and 2 pi. So what we get is 2 pi by 2 minus root e.